Previously we looked at the forming ionic compounds and we talked about some of those rules. So originally we said that they have to form a neutral ionic compound. So when we look at the individual ion of the two pieces or three pieces, whatever it is, they have to cancel each other out. So if we had, for example, like a magnesium chloride, Mg goes to a 2 plus and Cl, the chloride, goes to a 1 minus. So we would need a second minus, and therefore the formula would be MgCl2 to neutralize out. The other thing is that we do not carry subscripts from a reactant to a product. So for example, if we had hydrogen and it reacts with something else, it doesn't mean that because on the left we had hydrogen gas, which is H2, that we're going to have an H2 on the right. The subscripts don't necessarily carry over. The other one is that we always balance the equation last. So we do the first step, we make sure that they're neutral ionic compounds, we don't worry about the subscripts, then once we've got the full equation, then we balance it. So that's our order of predicting a reaction. There are a few different types of chemical reactions that we're going to look at in this lesson. The first one is decomposition, then we look at thermal decomposition and what that's implication is, then we'll look at combination, precipitation, and then the last two are the bigger ones where we look at reactions with acids, so like acids and metals, acids and bases, things like that, and then we look at reactions with oxygen, so combustion, respiration, and corrosion. The first one is acids with bases, and we call this a neutralization reaction because when we add an acid and a base, if the concentrations and the volumes are right, they basically cancel each other out and you no longer have either an acid or a base remaining. What you do have though is a salt plus water. So the general formula for these neutralization or acid and base reactions is acid plus base goes to water plus salt, or we could say an H2O plus a salt. And it's relatively easy to figure out what the salt is going to be just by elimination. Here we had hydrochloric acid and we added a sodium hydroxide. So this is the base, this is the acid. We end up with water always, we know that, and we're going to end up with a salt. So we've already used a hydrogen or maybe both hydrogens, and we've used an oxygen. So if I look at the only things left that I haven't used the Na and I haven't used the Cl. So process of elimination tells me that NaCl is going to be the product. I would check that it's neutrally ionic. So Na goes to a plus, Cl goes to a minus. That's all good. And then the last thing I would do is go across and balance if I needed to. And in this case, I don't. Acid with a metal is producing a salt and it's producing hydrogen gas. So rather than salt and water, when we add a metal to an acid, it dissolves it, creates a lot of bubbles, and those bubbles are actually hydrogen gas. So again, we can figure out what that salt is by elimination. If we know that it's making H2, we can look at the left-hand side, remove the H's, and sort of figure out what that salt is going to be. So remember that an acid and a base is salt plus water, acid and a metal is salt plus hydrogen gas. Next one is acids with carbonates. So a carbonate is anything that has this CO3 aspect to it. So calcium carbonate, you could have magnesium carbonate. Anytime you see a CO3 in the equation, it's a carbonate. And if we add an acid to that, what we get is we get a salt and water from before, but we also get carbon dioxide. And the reason this is because carbonates are actually a type of base. So we still have our acid and base reaction, which is the salt plus water, but because it's a special type of base, it's a carbonate base, we get our carbon dioxide. So if you still remember salt plus water as acid base, carbonate produces carbon dioxide, so CO2. And again, to figure out what the salt is, you know you've got H2O, you know you always have CO2, carbon dioxide. Process of elimination will figure out what that salt should be. Decomposition is the next one. Decomposition is when we have a single reactant and it just breaks down into multiple products on its own. So if we had some compound XY, without adding anything to it, it just kind of decays, or what we call decomposes, into X plus Y, whatever those two pieces are. For example, we could have the decomposition of water. So we have H2O and it decomposes into 2 lots of hydrogen gas and 1 oxygen molecule. Again, you can see that they've balanced it. We've got our H2s and O2s because that's the form that they're always in. and they've chucked the 2 in to balance out this. So we've got 4 and 4. Thermal decomposition is the same concept, but this decomposition reaction only occurs when we apply heat. It's not just going to do it on its own. An example of this, which is very common but often not understood, is sodium azide. And sodium azide is the chemical used in airbags. So what happens is we add a small amount of heat through a filament or a small chemical reaction or a small explosion in the airbag. That provides the heat needed for it to decompose, and then the sodium azide rapidly decomposes into sodium and nitrogen gas. And the nitrogen gas is what actually inflates the airbag. So you can see our chemical equation here. We've added the coefficients later to balance out, but I've got this thing, which is my sodium azide, and remember our state symbols. It's a solid, produces solid sodium and nitrogen gas. This is a bit of a diagram of how the airbag works. It has its sensor in it. When it detects a rapid acceleration or deceleration, it triggers the computer to then trigger the reaction. It heats the element, sets off the sodium azide, inflates the airbag with its nitrogen gas. So this symbol here is actually our gas form. Combustion is the next one. Combustion is just referring to burning stuff. So a substance that burns in oxygen to produce light and heat is a combustion reaction. This means it's exothermic. Exo means on the outside, so exothermic, it's giving off energy, it's giving off heat to the outside, it's giving away that energy. When we write the chemical equations for a combustion reaction, we just write plus oxygen. So we don't write plus fire or plus heat or anything like that. We use the symbol just plus oxygen to note that it was a combustion. So for example, we take a hydrocarbon here, C5H12, we add oxygen to it, which suggests that it's burning, and that produces CO2 plus H2O. So in this case, this is not hydrogen, this is a hydrocarbon, which is this thing. So hydrocarbons can be fuels basically. So butane, octane, propane, etc., are all examples of hydrocarbons, things that have hydrogen and carbon in their chemical structure, and they're all flammable. So we add oxygen to it, and we get this dihydrogen monoxide, which is actually just our water, plus CO2. It's really important to note that if we add O2 and lots of it, we call this complete combustion. This is when it produces carbon dioxide and water. So carbon dioxide is the important aspect here. If we look at another case where we don't have a huge amount of oxygen, we call this incomplete combustion. We didn't have enough oxygen to have a perfect burn, and in this case, we produce carbon monoxide and water. So we've always got the water, but if we've got lots of oxygen, we get carbon dioxide, and if we don't have enough oxygen, we get carbon monoxide. And this is really important because in automotive applications, when we're burning fuel, then we have to consider the fact that we don't want to produce this toxic carbon monoxide. We want carbon dioxide, which is still not great for the atmosphere, but at least it's not toxic to everything. Combination is the next one. This is like the opposite of the decomposition reaction, when two things combine to form a single product that's not necessarily a reaction. So we take this X plus Y, and it just goes to an XY. An example of this is the formation of water. So we have our hydrogen gas and our oxygen gas, and these are just attracted to each other, they bump into each other, and then they form water. So it's not a chemical reaction as such, it's just a combination reaction. Respiration. This is a very, very common one. It happens in the cells of all living things. Respiration is when we take glucose and oxygen, and it goes to carbon dioxide and water. So on the left, we've got our C6H12O6. That is the chemical formula for glucose. We add our oxygen, we get our CO2 plus H2O, and then they've balanced out the whole equation to give us the respiration equation. So as long as you can remember that we have glucose and oxygen goes to carbon dioxide plus water, you should be given that, or at least given glucose, because that's a complex structure, and then it would just be a case of balancing everything out by slapping all these sixes in front. The energy released by this is exothermic. So that energy is released in the cell, and this is used by the organism, used by us, etc., to actually harness that energy. You can see here, we get our glucose, we add our oxygen, and in this case, we get our carbon dioxide, water, and in the human body, what we want is this ATP, adenosine triphosphate, and this is the energy that we use. So we use this energy through the respiration. We take in the sugars, we add the oxygen through the lungs, and we produce this process. Corrosion is the next one. Corrosion is when a metal reacts with an oxygen in the air to form a metal oxide. We often just call this rust. So we take a metal, we add oxygen, we get a metal oxide. This is kind of using our ion formula. If you have a metal, say magnesium, you add oxygen to it. Remember, we always name it as the metal first, so it would be magnesium, and the oxygen or the non-metal becomes the oxide or the ide type word. So we would have Mg plus O2 goes to MgO or MgO2, whatever the formula is. But magnesium oxide would be the product there. And this is just what rust is. So rust is just a chemical reaction. It's very slow, but it is a chemical reaction. It's actually exothermic. So rust, or that oxidation reaction, the corrosion, is giving off heat. But because it's such a slow process, the energy that, or the heat energy that is released is actually basically undetectable because it takes so long to do. But it's actually giving off heat. So it's the world's worst heater. Have a go at these. So here I've given you a whole range of different reactions. I've even told you what they are in some cases. So acid plus metal, this is sulfuric acid added to this element, which you can look up. I want you to tell me what it would produce. So it's an acid and a metal. You can look at the slides before to know what it would actually produce in terms of what's the general formula, and then eliminate to figure out what they would be. Then we've got a combustion reaction, another type of combustion reaction, a metal solution. So we've got a magnesium plus a aluminium chloride, acid and a base, water goes to something. So what kind of reaction might this be? If we're not adding anything, there's no heat, etc. And then we've got an acid and a carbonate. So pause the video here, have a go at these questions. Remember the rules that it needs to be neutrally ionic charge, subscripts don't have to carry over, and then balance both sides last. Use the link in the OneNote or the lesson slides, which is the quizzes link. This will give you some revision questions about the topics that we've covered so far. There is also a worksheet, chemical reactions worksheet, which we'll start looking at. Work on that as well.